So in today's class, we'll start with IP routing. So we have completed our understanding on what is VLAN, what is switching, how switches work, right? How MAC addresses are used to forward data in a switch environment. What is an IPv4 address? What is a subnet? What is subnetting, etc. Right. So with all that knowledge in hand, let us move to the next major topic in networking, which is called as IP routing. So just like you have switching, where a device called switch is used to forward the traffic, right, based on the MAC addresses which is present in its MAC address table. Similarly, IP routing, okay, IP IP routing is again is very similar to switching, but instead of a switch, there is a device which is called as a router. There's a device called router which is present in the yeah which we basically use. Okay, router is what the device we use for routing. Router in diagram basically no in a switch is basically drawn like this. Okay, switch, right, and a router is basically written or drawn like this in a circular fashion. But in textbooks or in document purposes, we write a switch like this. We show switch like this and router in this form. This is how a router is shown in documents, and this is how a switch is shown in documents. Right. Anyhow, the working of a router is very similar to that of a switch. Okay. So let's go back to our understanding of how switch forwards data. Okay. So we know that there are three types of traffic in a switch environment. One is a unicast, right? A unicast. Second is a broadcast. Second is a broadcast, and the third is unknown unicast. Right? These were the three type of traffics that we saw in the switch. So based on the MAC address table of a switch, based on the MAC address table of the switch, where we have MAC address and port number mentioned, right? Uh, where we have a MAC address and port number mentioned, right? So a unicast traffic, we know that in a unicast traffic, we have a source MAC, right? We have a source MAC and we also have a destination, right? We have a source MAC and we also have a destination MAC. We have. So, which font looks better, this thin one or the thicker one?
A thicker one looks better.
Thicker one. Okay. So source MAC and destination MAC, right? So we have a source MAC and destination MAC, and the destination MAC. We know that the switch forwards data based on the destination MAC. The destination MAC, if the destination MAC is present in the MAC address table, right? So it will check the port out of which it should send the data, and the switch will forward the data, right? Broadcast, we know that a broadcast is a MAC address, a specific MAC address where it is written as FFFF, right? It is basically written as all Fs, right? And this particular broadcast MAC address is not necessary to be present in the MAC address table of the switch, right? So the destination MAC in a broadcast packet will be all Fs. The MAC address will be all Fs. The switch will understand that it is a broadcast and it needs to forward out of all the interfaces that it has connection to. Then there was an unknown unicast. With an unknown unicast, it meant that it was a unicast where it had a source MAC, and it also had a destination MAC. Right? However, this destination MAC was not present in the MAC address table of the switch. So when the destination MAC is not present in the MAC address table of a switch, the switch will basically forward it out of all the interfaces. Right. This was the basically the working of this switch with three different types of traffic. But for a router, okay, for a router, it has only two types of traffic. Not two types. I wouldn't say it's a type of traffic. It has two treatments for a traffic. Okay, I would say it treats. Okay, it treats the traffic. It treats the traffic in two fashions. Okay, first, okay, accept the traffic, accept the traffic, and forward it. Okay, and forward it. Then the next is drop the traffic. Simple. These are the only two kind of treatment that it does for a particular traffic, the router. And with what or what on what basis does it do? Is accepting the traffic and forwarding it or dropping the traffic is based on what? Is based on, again, we have learned IP address in the past few sessions. We learned IP address. So routers, just like switches deal with MAC addresses, routers deal with IP addresses, right? Routers, they deal with IP address. Okay, so the the treatment of the traffic to either accept or drop the traffic is based on the IP address, and that also the destination IP address. Okay, the destination IP. This is not DIP. It's, I've written it in short. Destination IP address. Okay, the destination IP address. So router needs to check the destination IP. Now, when I say the router needs to check the destination IP, yes, the router also has a kind of a table. Just like a switch had a MAC address table, a router also has a routing table. It has a routing table, okay, which looks very similar to a MAC address table, where it will have a destination IP address, okay, and the exit interface that it needs to send the data out of. Okay, there is one more column or one more column that it checks, which is the next hop IP address. We'll talk about the next hop IP address. We'll talk about exit interface destination IP in a while. Okay, so a router will check the destination IP in its routing table. And if the destination IP is present in the routing table, it will check the exit interface through which it needs to forward the data. Okay, so suppose a router is over here, right? And a packet comes into its interface. For example, this interface. Okay, with a destination IP, for example, of X, destination IP X. If the destination IP X is present in the MAC address, sorry, MAC in the routing table, it will check through which exit interface should it forward the data, and it will forward the data out of that interface. Okay, so this was the first criteria where it will accept the traffic and forward it, which is the condition where it drops the traffic. So if this destination MAC address, if the destination MAC address of X, if the destination MAC address of X is not present in the routing table of a router, if the destination IP is not present in the routing table of a router, it will drop the data. It will drop the data. Unlike a switch, where if the destination MAC is not present in the MAC address table, it will broadcast it out of all the interfaces. A router does not do so. If the IP address, destination IP address is not present in the routing table of a router, it will drop the data. Basically, it will not even accept the data. It will accept it. It will check the destination IP in the routing table. But if it does not find the IP address in the routing table, it will not forward the data. It will just simply ignore it, or discard it. That's the function of router. Okay. So as I said, router works in two fashion: either accept the traffic and forward it, or drop the traffic completely. And it is based on the IP address. And if the IP address is present in the routing table, it will accept and forward it. And if the IP address is not present in the routing table, it will drop the traffic. Clear? Any question of what a router and how does it forward the data? Okay. Now, for a switch, we studied when we were discussing switch, that switch populates its MAC address table with the help of receiving traffic. Okay. So again, let's have a recap. This is a switch. PC, multiple PCs are connected to the switch. PC number 1, 2, 3, 4. Right. So when PC number 1 forwards the data to the switch, what the switch is going to do? Switch will read the switch will read the source MAC address, right? It will read the source MAC address 1111, and it will populate the MAC address table with the interface number on which the data was received. Similarly, when PC2 sends the data, it will read the source MAC address and the interface that it received the data on. So a switch doesn't have to do anything. All it needs is that the end device or any data should be received on a particular interface, and that data should have a MAC address. And using the source MAC address, this switch populates the data or the MAC address table. This is what a switch does. Okay. However, for a router, this is not true. All right. So for a router, this is not true. All right. Now, on a router's routing table, okay, when a data is received, this is a router. Okay. Let's say it is connected to multiple PCs. For example, in real time, obviously, a router is not connected to PCs. A router is never directly connected to a PC. But just for this example, I have connected a router to multiple PCs. PC number 1, 2, 3, and 4. Right. Now, PC number 1 sends a data. Now, when we are talking about receiving or sending data, in our discussion with the switch, we were talking about MAC addresses. Now, instead of MAC addresses, we will shift our focus on IP addresses. So assume that PC number 1's IP address is 1.1.1.1. PC number 2's IP address is 1.1.1.1.2. Let me make it 2.2.2.2. PC3's IP address is 3.3.3.3, and 4 IP addresses 4.4.4.4. Okay. Now, when PC number 1 sends a data, for example, to PC number 3, so it will have a source IP of 1.1.1.1, a destination IP of 3.3.3.3. Okay. Source IP and a destination IP. Now, this packet or this data is received by the router. And we just discussed, the router will first look for the destination IP. In a switch reads the source MAC address and it will populate its MAC address table. But for a router does not populate its routing table. Router never ever populates its routing table automatically. Either it should be done manually or using some routing protocols. The routing table of a router should be populated. So on a routing table, we have a destination IP column and we have the exit interface, exit interface column. Okay. So when this data is received by the router is not going to write the or router is not going to populate the MAC, populate the IP address saying 1.1.1.1 was received on interface number 1. No, this is not how a router works. Router never sees the source MAC address. A router will always see the destination IP address in the IP routing table. Okay, so if the IP address is present in the routing table, it will check out of which interface should it forward the data, and it will forward the data to PC number 3. But as I said, if the IP address is not present in the routing table, the router is going to drop the data. The router is going to drop the data. Okay. Now, the second question that comes into our mind is then how is router going to populate its routing table? I just mentioned a few minutes back that the router has to populate its routing table either manually or through a routing protocol. When I say manually, as admins, we have to manually populate the router's routing table. And if we are going for automatic population of the routing table, we have to go for routing protocols. All right. Now, with these things in mind, first we will see how to manually populate a router's routing table. A router's routing table. Okay. Now, when we say manually populate the router's routing table, we also call this as static routing. We also call this as static routing. So when anyone asks what is static routing, tell them that we are manually populating the router's routing table in order for it to forward data. Static routing. Okay. Now, let me draw two routers, R1. Okay. Then another router, R2. Okay. Then another router, R3. Three routers, R1, R2, and R3. All right. Now, for a router to forward data and to receive data, it needs an IP address. The interfaces need an IP address. Okay. For a router to forward data and for the router to receive data, the interface should have an IP address. Okay. So first condition, IP address is mandatory. Mandatory. Okay. Now, for understanding purpose and to keep things very easy, you don't have to assign random IP addresses to the router interfaces. I'll give you or I will tell you a very simple way just for practice purpose. Obviously, in real time, you will have different IP addresses when you're working on the router. But when we are practicing or when you are explaining to someone, use this IP address convention because first thing, whatever I'm going to tell you, the IP address convention, first thing, it removes a lot of like no what do you say lot of ink. First of all, it basically removes a lot of ink. When I say removes a lot of ink, I don't have to write the IP addresses of the router. I know what the IP addresses are for the routers. Okay. Second, it clean or it keeps your topology very clear and crisp. Okay, so this is my IP address convention. And what is that? On R1, the IP address that I assign is 12. Why 12? Because this is between R1 and R2. So 1, 2, 12. So now you know that the IP address that I'm assigning is 12. This is the first octet of that IP address. The next is 0, 0. Okay. Then last is 1. So this is between 1 and 2. This IP address is between 1 and 2, and it is on 1, 12.0.0.1. So this is the IP address on R1. Now the IP address on R2, we can write it as 12.0.0.2. So between R1 and R2, and this is on R2. So on R2's this interface 12.0.0.2. Similarly, for R2's interface, which is facing R3, we will write it as 23 because it's between R2 and R3. 23.0.0.2. Why? Because it is on R2. On R3, we can say the IP address as 23.0.0.3. 23 because it's between 2 and 3, and 3 because this is R3 router. All right. So similarly, if you just simply expand or extend this particular network, okay, this is R5, for example. So between R3 and R4, you will write it as 34.0.0.3. Here you will write it as 34.0.0.4. Here, because it's between R4 and R5, 45.0.0.4, and here 45.0.0.5 because it's between 4 and 5, and this is on 5. Simple IP address convention. And while practicing on the lab also, you can use the same convention. And to explain someone also, you can use the same convention. It will be easier for you to understand. It will be easier for you to explain someone as well. And it will be easier for you to practice also. So many people just randomly write any IP address because it's 1. So they use 11.1.1.1. Here this is 2. So they think 20.0.0.3, 30, 40, 50. You don't have to use so many different IP addresses. Just this particular IP address convention will save you a lot of time. You don't have to memorize the IP addresses when you are dealing with big topology, and when you're practicing with big topology. You don't have to memorize the IP address. You know what the IP address is going to be. Okay. Any question of how the IP addresses are assigned? What IP addresses I will be using? Any question with that? Okay. All right. Now here, R1, R2, and R3 are connected together. All right. Now, the first thing is that when you assign, first thing you have to assign IP on the interface. IP on the interface. Okay, let's assume that we have assigned IP on the interface. How do you assign IP address on the interface? I will show you. Okay, now the moment you assign IP address on a particular interface, the router, okay, router's routing table for that network is populated. Okay, meaning that here, let's assume that I assign the IP address 12.0.0.1 on this particular interface of the router. R1 will automatically know that it is connected to the network 12, and we are going to use a default mask, so /8. It is R1. This interface is connected to 12/8. It will automatically know, and it will automatically populate the routing table of the router, saying that if 12001 is part of 12/8. Please listen to this carefully. 12001 is part of 12/8 network. And to reach any IP address of 12.0.0.0/8 network, it needs to forward the data out of this interface. Okay, it needs to forward the data out of this interface. Okay, now it will be better if I explain it with practical as well. Okay. So this tool, okay, this tool is called as GNS3. You can see on the left hand top corner, it's written as GNS3. This tool is an open source tool. You can just simply Google it saying GNS3. You can freely download this software. You don't have to create a login password. You don't have to create an account. You can just simply download the, probably you will have to create an account, but it's free to use. Okay, it's an open source. Anyone can download it. And how to download and how to install these images, I will show you in a different class. Okay, so these routers, once you install the software, you will not find these routers in the tool. You will have to add the router images in order for this tool to process it. And where will you get these images? How do you install these images to the tool? I will show you that in a separate class. Okay, but for today, let's just go through the practical as of now. Okay, so what I will do, I will open the CLI of all these routers. Just like we had CLI for a switch, we will also have CLI for the routers as well. All right. So if you had noticed, whenever we powered on a switch, we saw some information, right? What kind of information? What is the switch about? What kind of software is it running? What is its MAC address, etc. There were all those information. Similarly, when you power on a router, since this is a virtual router, you are not finding too much of information. But when you power on a real router, you will find a lot more information. What kind of router is it? What is the model? What is the software? What version is it running? Etc. All that information will be found in the real router. But since this is a virtual router, you won't find much of an information. But anyway, even though it is a virtual router, it will help us clear a lot of theoretical scenarios that we are going to study. Okay, and if you notice that our router's CLI also looks very similar to switches CLI as well. Okay, in a switch we will see we found switch hashtag, right? Similarly over here you can see R1 because that's the router's name, R1 hashtag. Okay, so this is again the privilege mode. This is the router's privilege mode. You have a user privilege mode as well. Sorry, you had the execution mode. Then you had a privilege mode in the switch. Similarly, this is the privilege mode of a router, right? So now on a router, we will assign IP addresses first. And how to assign IP address? Let's see that. In a switch, when we had to configure something on the interface, we had to go for the interface configuration, right? Similarly, on a router, also we will go on an interface configuration, going into the configuration terminal, right? Then what interface do we need to configure? Interface fast Ethernet 0/0. Over here, this is fast Ethernet 0/0 and enter. And to assign IP address, to assign IP address, guys, give me a minute. So just like switches interface configuration, we will go into the router's interface configuration. Interface fast Ethernet 0/0. And obviously, if we press question mark, we will have different types of command lines that we can execute after that. Okay. So what we will be executing? We will be executing IP, interface internet protocol configuration commands. Right. We will be executing this. So IP. Then again, if we press question mark, we will have address. We will set the IP address of an interface. Okay. So IP address, then again question mark. Then it asks, what is the IP address that you want to configure? Right. So we will set 12.0.0.1. I just told you how the IP address convention will be. This is between 12, 1 and 2. So 12 in the first octet, and this is R1's because we are configuring this on R1. So it will be 1. Right. Then again question mark, IP subnet mask. So whenever we configure an IP address, we have to configure it with the address mask or the subnet mask. So we will keep it as the default one, 255.0.0.0, and press enter. That's all. But doing so, is just assigning an IP to the interface. And to check the IP address that we have assigned on this interface, we will execute the command show IP interface. Okay, show IP interface will, sorry, show IP. Okay, we can check show IP interface as well. But with show IP interface, what happens is that it will show us all information of all the interfaces of the router. Here we just use one interface of the router. But if you see here, when I do a show IP interface, it is showing me all the interfaces that are present on the router. Right? You can see it says internet protocol is disabled. Okay, line protocol is down, like that. So this is not required. All this information is not required. Right? So instead of this detailed information with unnecessary lines, we will cut it down to a very brief of it. So show IP interface, we will write as brief. And we can see everything has come down to a neatly made columns and rows. Right. So here again, interface, we can see fast internet 0/0, and the IP address is 12.0.0.1. Method. How did we assign this method? How did we assign this IP address? We assigned this IP address manually. Status is administratively down. Protocol is down. Now, what does status and protocol mean? Status administratively down and protocol. What does this mean? It means that though I have connected a link on the router, I have connected a link on the router. Physically, the router has, or the interface has a link. You can see on 0/0, there is a cable that is connected. However, the status is administratively down, meaning that cable is there. However, the data will not pass because the status of this particular interface is administratively down. Now, for the data to pass, we have to make this interface as up. Here it is down. We have to make this as up. So configuration terminal interface fast Ethernet 0/0. Then what we are going to do, we will write no shut down. No shut down. Okay. Now when we do a no shutdown, you can see it throws a message. It says that fast Ethernet 0/0, the state has changed from the state has changed to up. Line protocol is also up. Okay, so this thing and the status, it was administratively down, it has changed to up. Protocol, which is the line protocol, it is also up. Now let's check the same command. You will see now the status is up and the line protocol is also up. Now what does line protocol mean? Status means yes, the data can pass. However, what does protocol or line protocol means here? Line protocol means that, okay, let me, I don't have the router in hand right now. What can't I mark? Okay, anyway, so when you connect a cable into these slots, okay, into these slots, okay, so you have to make it as administratively up. We just saw how to make it administratively up, okay, and to make it as administratively up, we have to give the command no shutdown. Now when you do a no shutdown, that means now the data can pass. However, for the data to pass, there should be some some means for it to pass. Means meaning that the IP, when we were discussing about first demo session, I showed you or I gave you an example of what an IP means. IP is like the road that is already laid down by the government. Similarly, over here, the line protocol is the road. It can be any, it can be a road. From networking point of view, it's not a road. It's like a signal. Is this signal okay? The data can pass. However, is this signal okay to sell? Is like is the, or you can say like the road is open. However, the checkpoint, you know, you have a checkpoint there. Is the checkpoint also open? That checkpoint is line protocol. If the checkpoint is down, you cannot pass the road. The vehicle cannot pass through the checkpoint, right? If the checkpoint is open, like whenever we pay fast time, like you have a checkpoint that comes down, like there is a bar that comes down, right? So if the bar is down, you cannot cross. If the bar is up, you can, the data can flow, right? So over here, the administratively up status means that the road is open now. The road is open, but if the line protocol is down, that means the bar, that rod is down and you cannot pass the data. But to make the line protocol up, if the line protocol is also up, the road is okay. The road is open and you can drive on the road. So similarly, in our networking or in this particular thing, status is like the road and the protocol or the line protocol up means the bar is also up. Okay, now the data can pass freely. That's what it means. So sometimes you may see that the status is up, but the line protocol is down. But the line protocol is down. You may see such scenarios as well. Okay. When do we see such scenarios? We will discuss that later. But if we have to always make sure that the status is up, the protocol is up in order for the data to pass. All right. So As per our thing, we just saw how to assign an IP address on the interface. The next routing table for that network is populated. Let's check that. To show the to show or to find or to look at the routing table of a router, you have to type the command. In for to check the MAC address, we have to write show MAC address table. Similarly, to check the routing table, we will write show IP route. Show IP route. Now, in Cisco, in Cisco, the routing table does not look like a table. It looks like a line of like no, it looks like a paragraph. Looks like a paragraph. It's not. It does not actually look like a table where it has rows and columns. But a MAC address table looks very decent. It has rows, it has columns, etc. But in Cisco, this is I'm talking from a Cisco perspective only. In Cisco, the routing table looks like paragraph. But if you go to other vendors and if you check their routing table, you may find columns. The routing table actually looks like a table where it has router, where it has the IP, where it has the IP column, it has the exit interface column, etc. Beautifully drawn. But in Cisco, it is written in form of paragraph. Okay. So to check the routing table, we will write the command show IP route. Okay. Now, as I said, the moment you assign an IP address on the interface, the routing table is populated. So over here, what IP address I assign? I assign the IP address 12001, correct? So, and I assigned this interface, this IP address on fast Ethernet 0/0. And what kind of subnet mask did I use? I used the subnet mask of 255.0.0.0. So the router automatically knows that this interface, fast Ethernet 0/0, is connected to 12.0.0.0/8 network. And if I want to reach any IP address in the address range of 12.0.0.0/8, I can send the data out of this particular interface. And that is what the routing table is saying. It says to reach any network 12.0.0/8, I can send the data out of fast Ethernet 0/0, which is directly connected. This whole network is directly connected on this interface. So if you try to reach 12.0.0.1, 12.0.0.2, or 12.255.255.254, this this is the interface through which the router is going to forward the data. Okay, so we know that 12.0.0/8 network, 12.0.0.0/8 meaning 255.0.0.0. This is the network, right? So starting from 12.0.0.1 up till 12.255.255.254. These IP addresses, to reach these IP addresses, the router is going to use fast Ethernet 0/0 interface. That is what it is trying to say. So the moment you assign an IP address on any interface, the routing table of the router is populated with the exit interface as that interface. And the network that the IP address is connected to, that is also known to the router. Clear? Any question till here?
No, till it's fine.
Okay. Now let's go to R2. On R2, we will have to assign IP addresses, configuration terminal, interface fast Ethernet 0/0, IP address. Fast Ethernet 0/0 is the interface that is facing R1. IP address 12.0.0.2, 255.0.0.0, and a no shutdown. Okay. Then you do not have to exit. There is no need for you to exit and then write the next interface fast Ethernet 0/1. You can write this, it's okay. However, you can directly go to other interface by writing that interface number over here itself. So previously I was on interface fast is 0/1, but inside this interface, I change the interface to fast Ethernet 0/0. Now, whatever changes I make will be for interface fast Ethernet 0/0 of R2 and not for 0/1. All right. Now, going back to fast Ethernet 0/1 once again. Okay. We will write the IP address. IP address. This is facing R3. So 23.0.0.2, 255.0.0.0, and a no shut. Okay. And now let's check the routing table of R2. Show IP route. Show IP route. So over here, you can see R2. R2, you can see R2 is connected. On R2, we configured two different IP addresses. We configured 12.0.0.2 and 23.0.0.2 with an address mask of 255.0.0.0. So R2's interfaces are connected to two different networks. And now R2 knows how to reach those networks. See here, you can see 12.0.0/8 is directly connected on 0/0 interface. That is this interface. Similarly, 23.0.0/8 is directly connected on 0/1. That is this interface. So any IP address that belongs to this network or this network, R2 knows how to send them. Meaning that any data that comes for this network, R2 knows to forward it out of this interface. Any data that comes for 23 network, R2 now knows how to forward. It has to forward it out of 0/1 interface. All right. Now on R3, configuration terminal, interface faster than 0/1, IP address 23.0.0.3, 255.0.0.0, no shut. Okay. So show IP route. We will see R3 now knows how to reach 23 network. Now let's see something interesting. R2 knows how to reach 23 network. R3 also knows how to reach 23 network. That means R2 knows how to reach R3. Similarly, R3 also knows how to reach R2. Right? Similarly, R1. R1 is connected to 12 network. It knows how to reach 12/8 network. R2 also knows how to reach 12/8 network. That means R1 can send data to R2. R2 can send data to R1. Similarly, R2 can send data to R3. R3 can send data to R2. Right? I hope this is clear. Any problem understanding this part?
No, it's that's fine.
Right. Now let's try to ping. Ping is a connectivity check command. Ping, again, ping is a connectivity check command that we have been seeing in the switch as well. So ping from R2, I will try to ping R3's IP address 23.0.0.3. Okay, we can see it pinged. We are seeing a success. We can see success. Exclamation mark means success. We are able to ping. You can see success rate is 100%, 5 out of 5. Right. Now let's try to ping R1's IP address. Ping 12.0.0.1. Okay. So it is a success. R2 is able to reach R1. Now, how is R2? How is R2 checking this thing? We'll see it. How is R2 making this decision? Okay. So let's go to our diagram. R1, R2, R3. R1 on R1's routing table, it knows how to reach 12/8 network through fast Ethernet 0/0, which is this interface. 0/0 interface. This is also 0/0 interface. This is 0/1 interface. This is 0/1 interface. Okay. R2 knows how to reach again. R2 knows how to reach 12/8 network. Okay. R2 knows how to reach 23/8 network. R3 also knows how to reach 23/8. So on R2, when I did a ping, when I did a ping of 23.0.0.3, what R2 is doing, R2 is creating a packet. It is creating a packet with a source IP, with a source IP of its own IP address, that is 23.0.0.2, a destination IP of 23.0.0.3. Okay, so 23.0.0.3. Now, what it's doing is it is checking 23 how to reach 23.0.0.3. Does it know how to reach 23.0.0.3? It knows how to reach 23.0.0.3 via this network. 23.0.0.3 is part of 23/8 network. And to reach any IP address, and to reach any IP address which belongs to 23 network, it needs to forward the data out of 0/1. So it is forwarding this data out of 0/1 and it reaches R3. All right. Now, R3, upon receiving this data, it accepts the data because this IP address belongs to R3. 23.0.0.3 belongs to R3. So it accepts that data. Now it's time for R3 to respond. When R3 responds, the source IP now is going to be R3's IP address 23.0.0.3. Destination IP now it is going to be 23.0.0.2. Right? 23.0.0. Now, what R3 is going to do? R3 will check 23.0.0.2. Which network does it belong? It belongs to 23/8 network. And to reach any IP address which belongs to 23/8 network, it needs to forward the data out of 0/1. And hence, R3 is able to forward the data to 0 to R2. And that is why we were able to see this ping. This ping. All right. Similarly, for R1 as well, when R1 does a ping, sorry, on R2, when we do a ping of 20, sorry, not 23, 12, 12.0.0.1, it creates a source IP of 12.0.0.2, which is this interface IP. Okay. And it creates a destination IP of 12.0.0.1. Then it checks to reach 12.0.0.1. How can I reach? What network does 12.0.0.1 belong to? It belongs to 12/8. And to reach any IP address that belongs to 12/8, it needs to forward or send the data out of 0/0 interface. Right. So R1 received it. When R1 received it, it will check the destination IP, which is R1's IP address only. Now R1 will respond. When R1 responds, it will have a source IP of 12.0.0.1 and a destination IP of 12.0.0.2. Okay, so R1 now checks to reach 12.0.0.2. Which network does it belong to? It belongs to 12/8. And to reach any IP address that belongs to 12/8 network, it needs to forward the data out of 0/0 interface. And hence the data now is sent to R2, and R1 and R2 now can ping each other. Can now ping each other. Clear? Any question? Understanding this part?
No, this totally is fine.
So this means that R2, R1, and R3, these three routers, they know about their directly connected networks. R1 is directly connected to 12/8 network. R2 is also directly connected to 12/8 network because their interface IPs belong to that network. Similarly, R2 knows about 23/8 network. R3 also knows about 23/8 network because the interfaces that they were configured for were part of 23 network. So when you assign or configure a particular IP address, you do not have to create a routing table or you do not have to populate the routing table of that router for that particular network, or for the directly connected network you don't have to do anything. So on R2, when we do a show IP route, okay, 23 network and 12 network are directly connected to R2's interfaces because the two IP addresses were 12.0.0.2 and 23.0.0.2, right? So that network, we don't have to manually populate. Now, where does manual population comes into picture? It comes into picture where I want to ping R1 and R3, where I want to ping or I want the communication between R1 and R3. Okay, so let's check. Let's go on R1 and try to ping 23 network, which is 23.0.0.3, which is R3's IP address. Okay, and we will see that it is not, the data is not sending, it's not pinging, right? You can see success rate is 0. And why is that so? Because when we do a show IP route, 23 network, 23003 network is not present in the router's routing table. And as we had discussed earlier, the two types of functioning of a router to forward a traffic is either accept the traffic or drop the traffic. Here on R1, we did a ping of 23003, but 23 network is not present in the router's routing table. And hence what it does, it will drop the traffic. It's not forwarding the traffic at all. That's what it means. And that's what the dot over here denotes, that it is not forwarding the data. Why? Because 23 network is not present in the router's routing table. Similarly for R3 also, if we try to ping on R3, if we try to ping 12.0.0.1, which is R1's IP address, it will not be able to ping because 12 network is not present in R3's routing table. Okay, R3's routing table, it is not present, and hence it is unable to forward the data. Okay, so it's very similar to like having a map, or someone comes and asks you, you are going on a road. Imagine that you are going on a road and someone comes and asks you, can you tell me how to go to Mumbai? Okay, if you know how to go to Mumbai, you will guide that person how to go to Mumbai. If you do not know how to go to Mumbai, you will be like, I don't know, please ask someone else. Okay, at least in human world, the person will go and ask someone else. But over here, when the router does not know how to reach Mumbai, he will drop the path. That's what happens over here. So how to make R1 and R3 reachable, or how to manually populate the routing table of R1 and R3 so that they can reach each other. Let's see that, how to do so. So what we will do, we will configure. We will go into the configuration terminal and we will manually populate the routing table, and the command is IP route. Okay, let me write the command first completely and then I will explain this command. IP route 23.0.0.0 255.0.0.0 and the and 12.0.0.2. Okay, this is the command. I have given I have written one command. So let me copy this command. Sorry, my computer got stuck. Give me a minute. So over here, what I said on R1 is that I wrote the command IP route 23.000.255.000.12.002. Okay, what does this mean? On R1, I'm telling R1 to create a an IP route table to create an IP route table for the 23 network with the address mask of 255.000. Okay, 23 network with 255.000 as the address mask. Okay, it can be a classful address mask, it can be a classless address mask as well. But over here, you always write the network IP, not the network, not the exact IP address. If you're writing the exact IP address, you will have to write the exact address mask as well. So over here, we are telling the R1, we are telling R1 to create an IP routing table or IP route for 23 network, which has an address mask of 255.000. And to reach this network and this address mask, it needs to go to 12.0.0.2, which is the next hop IP, which is the next hop IP. Okay, so 12.0.0.2 is the next hop IP to reach 23. Okay, we know that 12.0.0.2 is R2's this interface IP address. And for R1, this is the next hop. So we are telling R1 that if you want to reach 23 network, send your data to your next hop, which has an IP address of 12.0.0.2. This is what we are telling the router R1. And now let's check on R1 what or how does the routing table populates. Show IP route. Okay. Now you can clearly see R1 now knows how to reach 23 network. Okay. And it knows via 12.0.0.2. Via 12.0.0.2. Okay. To reach 23 network, it needs to send the data to 12.0.0.2. So in R1's routing table, there is a column for 23 network, and it knows how to reach 23 network by sending the data towards 12.0.0.2, which is R2's IP address. Okay, this is one way of configuring a static route. Second way of configuring a static route, let's do that on R3. Configuration terminal, interface, not interface, sorry, IP route. Now, on R3, we have to make R3 know about 12 network. We can see 12 network is not present. So we will use the 12 network over here, 12.0.0.0 with an address mask of 255.0.0.0. Now, instead of the next hop IP, we can give the exit interface itself. Okay, and the interface over here is fast Ethernet 0/1. Let me take you to the diagram. Here you can see this interface, fast Ethernet 0/1, is the interface through which R3 will send the data towards 12 network. So over here, let me again bring this on the diagram. So what I'm telling R3, create an IP route in its routing table for 12 network with an address mask of 255.0.0.0. And if you want to reach this 12.0.0.0 network, you need to send your data out of this interface, 0/1 interface. This is what I have told R3. On R3, I have told if you want to reach 12 network, send the data out of out of the exit interface, that is 0/1. Okay, so these are the two methods with which you can manually populate the router's routing table. Okay, so on R1 knows about 23 network. R3, let's check R3's routing table. Show IP route. R3 also knows about 12 network. Okay, R3 also knows about 12 network. Correct. Now let's try to ping R1 and R3. Previously we tried to ping, it did not work, right? We pinged 23 network or 23003, which is R3's IP address. It did not work. Correct. Let's try to ping now. Ping 23.0.0.3. Okay. And we can see a success message where success rate is 100%. Previously, the success rate was 0. Now, success rate is 100%. Let's go on R3 as well. Ping 12.0.0.1. We can see a success. We can see a success. So let's see how is it actually working. What is R1 and R? What are R1 and R3 doing? So when you do a ping 23.0.0.3, right? The router creates a packet with a source IP of 12.0.0.1, a destination IP of 23.0.0.3. Now, it checks 23003 in its routing table, right? Now, because we have manually created, we have manually created the IP route, telling that to reach 23 network or to reach any IP address of 23 network, you need to send the data to 12002. You need to send the data to 12002. Now, here there's a twist. It's not a twist, it's an extra step that R1 takes. We have mentioned to reach 23 network, you need to send the data to 12002. But does R1 knows how to reach 12002? Does R1 know how to reach 12002? Yes, it knows how to reach 12002 because 12002
Directly connected.
12002 is part of this network. Correct. 12002 is part of this network, and to reach this network, it needs to send the data out of this interface. So eventually the data is being sent out of the exit interface only. For 23 network also, the data is sent out of fast Ethernet 0/0, and for 12 network also, the data is sent out of fast Ethernet 0/0 only. Right. So over here, the router is doing two steps. First, it is checking the destination IP. How to reach the destination IP? That is the next hop 12002. Does the router know how to reach 12002? Yes, it knows how to reach 12002. And to reach 12002, it needs to forward the data out of fast Ethernet 0/0. So the data is forwarded to R2. Now, R2 receives the data, right? R2 receives this data, right? So R2 checks the destination IP, that is 23003, correct? And in R2's routing table, to reach 23003, 23003 is part of 23 network. And to reach any IP address that belongs to 23 network, it needs to forward the data out of 0/1, which is automatically present in the routing table of R2. We did not configure anything because the moment we configured the IP address on R2, this was automatically populated. So what R2 does, R2 will forward the data. R2 will forward the data to R3. R3 receives it. R3 will also check the destination IP. The destination IP is R3's interface IP only, right? So it accepts the data. It accepts the data, and in response, it creates its own packet with a source IP of 23003 and a destination IP of 12001. Correct. Now it needs to send this data. So it checks the routing table. So we have told R3 that to reach 12 network or any IP address that belongs to 12 network, forward the data out of exit interface fast Ethernet 0/1. So on R3 here, to reach any network of 12, to reach any IP address of 12 network, forward the data out of 0/1. So what R3 does, R3 will forward this data to R2. R2 will receive it. When R2 receives it, it will check the destination IP as 12.0.0.1. Now, R2 is already directly connected to 12 network. And to reach 12 network, R2 already knows that it needs to forward the data out of 0/0 interface, right? And hence it will forward the data out of 0/0 and it will reach R1. And it will reach R1. And this is how your traffic or data is flowing between R1 to R3 and back. Clear? Any question?
No.
No. So this is
While
how a
create
static route
this
is. Yeah.
static route,
Huh.
don't we give that wild mask? What is that called as?
No, we don't give wildcard mask in static routing. We give
Is in
wildcard mask only in routing table, routing protocol. So over here, we give the
OSPF,
IP
right? I guess.
in OSPF, EIGRP, ISIS, etc.
Okay.
So
Okay.
over here, we don't give wildcard mask, but we give the exact address mask.
Yeah.
All right. So this is how a static route is created. Two methods to use the next hop IP and to use the exit interface. Even if you use the next hop IP, eventually the router falls or eventually the router makes the decision of the exit interface only.
Yeah.
The next hop IP should be reachable. Then only the router can use the next hop IP static routing configuration. Otherwise, it will not be able to use. Right. So this is how we do static routing or manual routing configuration. Any question?
No, I think this is clear.
Right. So with this, we have come to an end of static routing. And tomorrow, we'll go ahead and understand few other features of routing, especially what is a ping, what is a ping packet, what is an ARP packet, right? So because these two are very important to understand how routing works, and mostly whenever we are working on IP routing, right, we will be using ping command a lot. So working of ping, working of ARP is very important to understand over here. So tomorrow we'll discuss that.
Okay.
So thank you, and have a great day. Yeah.
So thank you.
So today we will discuss about the Ethernet and the IP header. So in our previous few classes, we have learned what is a MAC address, how MAC addresses are used by the switches to forward the data. Similarly, what are IPv4 addresses and how IP addresses are used by the router forward data through static routing. We saw that, right? So in last class, I said we will discuss about ping and ARP, right? But however, moving towards ping and ARP, first I want to discuss the Ethernet and the IP header indirectly, meaning that the layer 2 header and the layer 3 header. Now, when I say layer 2 or layer 3 header, layer so when I say layer 2 header or a layer 3 header, so it means that I'm talking from the perspective of OSI layer model. Okay, so in our demo class, we saw there were 7 layers in the OSI layer model, starting from layer 1. Layer 1 is your physical layer, correct? Physical layer. Then you have layer 2, which is your uh, uh, Ethernet layer. Ethernet layer, right? Then layer 3 is your network layer. Then you have layer 4, transport layer, and layer 5, layer 6, and layer 7. Layer 7 is your application layer. Okay. Then this is your presentation layer. And then layer 5 is your session layer. Right. So these are the 7 layers in our OSI layer. So when I say we are going to discuss layer 2 header and layer 3 header, I mean to say that we will be discussing the Ethernet frame header and the IPv4 header. Okay, we are going to discuss these two headers today. And why is it important to discuss these two headers? It's because when we will be discussing the ping and ARP, right, we have to know those headers in order to understand the working of ping and ARP better. Okay, so it is important to understand these headers from an interview perspective as well. So going from all these perspectives, we will discuss what is a layer 2 and layer 3 header in today's class. Okay, so a layer 2 header. Okay, or your Ethernet header. So just like any letter that we write, right, any letter that we write, we always start with a from address, and then we have a to address, then there is a date and the salutation, like respected sir, madam, or whatever. Then we have the body of the letter, and then the thanking you, yours faithfully, etc., and then your name. Right? This is a general format of writing a letter. Correct. So if any of these fields of the letter is missing, for example, if your to address is missing from the letter, basically the letter is incomplete. Or if the date is missing from the letter, that means the letter is incomplete. You cannot send the letter forward. Similarly, when a switch, okay, when we are talking about switch and the Ethernet header, we will talk from switches perspective. So whenever a switch, right, it is reading layer 2 header, right, layer 2 header, which involves MAC addresses, okay, which involves MAC addresses. So the switch reads not just the MAC addresses, there's a huge format, not a huge, there's a small field or there is a small format of that layer 2 header which involves or which includes MAC addresses. MAC address is just one part of the layer 2 header. There are other fields also in the layer 2 header which we have not discussed till now, which we'll discuss in today's class. Okay, so this switch or imagine us humans as switch. For us, we are the important part of this letter is the body of the letter or the content that is inside the letter. What is this letter about and what is written here, right? Similarly, for this switch, this is important for the switch. Okay, this is the MAC address for the switch. However, there is all these formats are also present, or all these headers are also present. Okay, or all these fields are also present in the header of a layer 2 Ethernet frame that we will discuss today. So let me draw that header first. I will tell all these headers one by one. We have a preamble field, then we have a SFD field, then we have a destination MAC field, then we have a source MAC field, and then we have a type field, data field, and FCS. Right. So these are the fields in a Ethernet frame. In an Ethernet frame, these are the fields. Until now, we were looking at only the destination MAC and the source MAC field of an Ethernet header, but we did not discuss the other fields of an Ethernet frame. Right. If you had noticed when we were discussing VLANs, I was opening up the Ethernet header, and we were discussing only destination MAC and source MAC. But there were other fields also in the Ethernet header, which we did not discuss. Right. So those fields that we did not discuss, I have written in on the screen. So the first field, preamble. Okay, preamble is a 7-byte field. It's a 7-byte field. Okay, SFD is a 1-byte field. We have a destination MAC address. We know that it is 48 bits. 48 bits. That means it is 6 bytes. 6 bytes. Source MAC is also 6 bytes. Okay, and give me a minute. Let me open up. And let me check the size of the other fields as well. Okay, so you have 2 bytes and 4 bytes. Okay, this is a 2 bytes field, and frame check sequence is a 4 bytes field, and this varies from the data field varies from 46 to 1500 bytes. Okay, 46 to 1500 bytes. It varies between 46 to 1500 bytes. Now we will discuss each and every field in the header one by one. The first field, preamble. Okay, what is a preamble? Preamble, as I mentioned, it's a 7-byte field, and 1 byte of this preamble field, the format of that 1 byte is alternate ones and zeros. 1 0 1 0 1 0 1 0, and we know that 1 byte is 8 bits. Right? So you have 8 bits of alternate ones and zeros. Right? So this is just 1 byte. You have 7 such bytes. Okay, 7 such bytes. 7 bytes into 8 bits. You have 56 bits. That means 56 bits of ones and zeros. Every Ethernet header, every Ethernet header will start with 56 bits of alternate ones and zeros. This is the format of the preamble field. Okay, this is the format, or this is how a preamble is written in an Ethernet field. It's it is predefined. You cannot change it. Okay, it is predefined. You cannot change it. So in an Ethernet header, preamble is a field. Okay, whose format is 56 bits of ones and zeros, alternate ones and zeros. Okay, starting from one, ending with a 0, 56 bits. All right. Then you have a SFD field. SFD, which means start frame delimiter. Start frame delimiter is the full form of SFD, start frame delimiter. Start frame delimiter, as I mentioned, is a 1 byte field, and that also is an alternate ones and zeros. 1 0 1 0 1 0 1 0. Now, except for the last bit. So you may see that the 8 bits of a preamble field and the 8 bits of a start frame delimiter are same. Then what is the difference? The difference is the last bit of the start frame delimiter is not a 0, but a 1. But a 1. Okay. So 1 0 1 0 1 0 1 1. So if we add up this 56 bits and these 7 bits of the start frame delimiter, we get 63 bits. Okay, 63 bits of alternate ones and zeros. 63 bits of alternate ones and zero, and the 64th bit is a 1. 64th bit is a 1. So 63 bits of ones and zeros, alternate ones and zeros, and 64th bit is a 1. This total 64 bits includes, again, I'm repeating, the 64 bits of these 64 bits of your Ethernet frame is the preamble plus your SFD field. preamble and the SFD field. And what we have seen now is the format of your preamble and the SFD field. Okay. Now we understood the format of the field, but what does preamble and start frame delimiter do? What does preamble and a start frame delimiter do? Let's understand that with a topology. So this is switch number 1 and this is switch number 2. Okay. Switch number 1 has a MAC address of 11111 all ones, and switch 2 has a MAC address of 22222 all twos. Right. Now switch 1 is sending data to switch number 2. Okay. Switch number 1 is sending data to switch number 2. So it sends frame number 1, it sends frame number 2, then it sends frame number 3, and then it sends frame number 4. Okay. So it has sent 4 frames, 4 Ethernet frames to switch number 2. All right. Now, in each of these frames, the source MAC is going to be 1111 all ones. Destination MAC is going to be all 2222. Correct. So now switch 1 has sent all these frames. Frame number 1 is received by switch number 2. Frame number 2 is also received. Frame number 3 is also received. Frame number 4 is also received. And please remember, all these frames have the same source MAC address and also have the same destination MAC address. Same source and same destination. Okay. Now understand switch number 2's confusion. Let me go back to the diagram over here. Okay. Every frame, be it frame number 1, frame number 2, frame number 3, frame number 4, have the same destination MAC, have the same source MAC, have the same preamble, have the same source start frame delimiter. As I said, every Ethernet frame will have a preamble and a start frame delimiter field. Okay, every Ethernet frame. Okay, so the frames that are sent by switch number 1 will have all these 4 frames will have the same destination MAC, will have the same source MAC, will have the same preamble field, will have the same source start frame delimiter, will have the same type field, will have the same FCS field, will have the same data, Okay, so the problem of switch number 2 here is that how will switch number 2 identify which is frame number 1, which is frame number 2, which is frame number 3, and which is frame number 4? How, again, confusion of switch number 2 is how will it identify or differentiate switch frame number 1, frame number 2, frame number 3, and frame number 4? Because every Ethernet frame have the same fields in their Ethernet header. And hence the switch number 2 has the confusion. How is it going to differentiate which is frame number 1, which is frame number 2, and which is frame number 3 on 4? Right? I hope you get it. And in order to even understand it even better, let me open up Wireshark. Okay, Wireshark is again a tool. Okay, we will discuss Wireshark probably later in our session. However, let me just open up one example. Okay. See here. Over here, if you see the data, okay, over here, if you see the information that is being sent is all hexadecimal value. Everything is hexadecimal value. Okay, B8, B is a hexadecimal value. B, we know that is written is basically 11. Okay, 11, right? B8, B7. So for us human, it is B8, B7, DB3C. We can read it. But for a networking device like a switch or a router, they will convert it into their respective binary form, ones and zeros. And imagine the different combinations of ones and zeros that all these information will have. Correct. Different combinations of ones and zeros. So again, the same question comes, how is the switch, how is the switch number 2 going to differentiate between frame number 1, frame number 2, frame number 3, and frame number 4? That frame number 1 has started, frame number 1 is has ended. Now frame number 2 has started, it has ended. Then frame number 3 has started, it has ended. Now then frame number 4 has started and it has finished reading frame number 4. That differentiation, okay, the differentiation between frame number 1, 2, 3, and 4 is created by your preamble and start frame delimiter field. And how is it created? As I said, every Ethernet frame starts with a 7 bytes of preamble and 1 byte of SFD field. Frame number 1, frame number 2, frame number 3, frame number 4, each will have a preamble and an SFD field. So when frame number 1 is received by switch number 2, it starts to read preamble and SFD field. And when it starts to read preamble and SFD field, it will read 63 bits of ones and zeros. It will read 63 bits of ones and zeros, and finally the 64th bit in this SFD field will be a 1. Correct? This 64 bits includes your 56 bits of preamble, okay, and 8 bits of SFD, right? Where this last bit in SFD field is 1, which we discussed just now, right? So 63 bits of ones and zeros, and then 64th bit as well. So every preamble and SFD field in these frames will have a 63 bits of alternate ones and zeros, and the last bit will be a 1. So now frame number 1 is received by switch number 2. So when switch 2 reads frame number 1, it will read frame number 1's preamble and SFD field. So switch number 2 will know that a new frame is incoming. That is what the start frame delimiter says. A start of a frame. Start frame delimiter, meaning a new frame is starting. A new frame is starting. So switch number 2 understands that when it reads 7 bytes of preamble and 1 byte of start frame delimiter, it understands that a new frame is starting. Okay. Now switch number 2 reads preamble field, it reads start frame delimiter field, it reads the destination MAC field, it reads the source MAC field, it reads type field, it reads the data field, and it reads the FCS field. And it has finished reading FCS field. And immediately after, when it finished reading FCS field, it is reading the information present in frame number 2. It is reading the information of frame number 2. Okay. Again, in frame number 2, it will start to read 7 bytes of preamble and 1 byte of start frame delimiter. Again, switch 2 will realize, oh, frame number 1 is over. Frame number 1 is over. Now I am reading 7 bytes of preamble and 1 byte of start frame delimiter. That means a new frame is starting. A new frame is starting. So switch number 2, upon receiving frame number 2, it reads all the headers of frame number 2, and it finish reading frame number 2. Then immediately after, frame number 3 comes. For frame number 3 also, it will read 7 bytes of preamble field and 1 byte of start frame delimiter, thereby realizing that a new frame is starting. Frame number 2 is over. Now a new frame or frame number 3 is received, and switch number 2 is reading that. Switch number 2 finish reading frame number 3, and it receives frame number 4. When it receives frame number 4, again frame number 4 has the same 7 bytes of preamble field and 1 byte of SFD field, thereby letting switch number 2 know that a new frame has come and it needs to read the data of the new frame. This is the work of your preamble and start frame delimiter. It tells this switch or any networking device that when has a new frame starting, or when is a new frame starting, or when has the switch finished reading the old frame and it is starting to read the new frame. So every time a new frame is received, the networking device, it can be a switch or it can be a router, it first reads the 7 bytes of preamble field plus 1 byte of SFD field, thereby realizing that a new frame has been received and it is reading the new frame. This is the work of your preamble and start frame delimiter, which tells the networking device that a new frame is being read by the device. All right. We already know what is a destination MAC. We already know what is a destination MAC, what is a source MAC. Okay, because we in our section about switch or VLANs, okay, and even in the span and tree discussion, we know what a destination MAC and a source MAC does. Okay. A type field. Now, what is a type field? Okay, imagine that you have received. Imagine that you have received an Amazon courier. Okay, you have received an Amazon courier, and if you had noticed in that Amazon courier, there will be a to address, which will be your address, and there will be a from address, correct? And there will be a description. Description of what? Description of the package. What is inside the package? You can simply identify what is inside the package by reading this description and make out what is this package about. Correct? Similarly, that is what the type field does. The type field of your layer 2 header tells what kind of package, and here the package means data. What kind of data is inside this layer 2 header, and how is this layer 2 header working? So whatever, see here, we are discussing this over a Zoom call, right? So Zoom is running basically at the application layer. My application layer or the Zoom data, this video call, this screen sharing, etc. Everything is being shared, right? Everything is being captured and it is sent to the layer 6 data. Layer 6 passes on to layer 5. Layer 5 passes on to layer 4. Okay, it passes to layer 4. Layer 4 passes to layer 3. Layer 3 passes it to the layer 2. So all this data starting from layer 7 till layer 3 is basically the data which is inside here. This is your data. However, your Ethernet layer has visibility. Your Ethernet layer has visibility only till network layer only till network layer. Only till network layer. Okay. So in the data field or in the type field, okay, by reading the type field, the switch will understand what kind of layer 3 data is it carrying. What kind of layer 3 data is it carrying? Is it carrying an IPv4 data? Okay, is it carrying an IPv4 data? Is it carrying an IPv6 data? Is it carrying any routing protocol data? We'll discuss routing protocol later. Is it carrying any routing protocol data? Is it carrying an ARP packet? We'll discuss ARP later, as I said. Is it carrying a ping packet, etc. So the switch automatically, by reading the type field, understands that what kind of data is being carried in this data field. Okay, there are different types of data: IPv4, IPv6, routing protocol data, and ARP ping that I mentioned here. But these are different types of data. Okay, so the switch will understand what kind of data is being carried in the network layer. Okay, over here, what kind of data is being carried? Is it, again, let me write that down. Is it a ping packet? Is it an ARP packet? Is it an IPv4 data? Is it an IPv6 data? Is it a routing protocol data, etc.? All that information is given by the type field of your layer 2 header is given by the type field of your layer 2 header. All right. Now data, as I mentioned, I just gave an example of what can a data be, right? Then the last, frame check sequence, FCS. FCS, frame check sequence. Okay. So by the name, we can easily identify what does it do. It is basically checking the sequence of the frame. Okay. It is an easy mnemonic to understand what an FCS does or what a frame check sequence does. It's checking the sequence of the frame. However, that is not the real work of frame check sequence. Okay. So what does a frame check sequence do? Let us understand it. This is switch number 1 and this is switch number 2. Okay. So as I said, every Ethernet header will have a frame check sequence. So switch number 1 is sending some data to switch number 2, for example. Okay. And what switch number 1 will do, it will run an algorithm. Okay. What kind of algorithm? Even I do not know. Honestly, even I do not know what kind of algorithm it is. It runs an algorithm and comes with a value. Okay. For example, that value is 1, 2, 3. So this is the frame check sequence value. This is the frame check sequence value, which is added in the Ethernet header. And the data is sent to switch number 2. Switch number 2, upon receiving this Ethernet frame, it will read the preamble, it will read the start frame delimiter, destination MAC, source MAC, type field. And then it opens up the FCS field, frame check sequence. When it opens up the frame check sequence, it also runs the same algorithm. Okay. When it runs the algorithm, the value should be 1, 2, 3 for switch number 2 as well. If 1, 2, 3 or the frame check sequence value on switch number 2 is equal to the frame check sequence of switch number 1, that means the frame is correct. Meaning frame is not corrupt. Okay, frame is not corrupt, or frame is not corrupt. Frame is how can I say? Frame has, okay, the frame has correct integrity. Okay, or the frame has not been, okay, tampered with. Okay, the frame has not been tampered, or the frame has not been touched by any other intruder. Okay, it is not corrupt. That is what the frame check sequence basically does. Okay, and what if the value is different? Let's say instead of 1, 2, 3, let's say the value of frame check sequence on switch number 2 is ABC. That means frame is corrupt. The frame check sequence on switch number 2 and the frame check sequence on switch number 1 are different. That means the data is corrupt. And if the data is corrupt, okay, switch is not even going to open up this data, the data field. The switch is not going to open up this data field, and it will discard the packet or the header. That means frame check sequence on both the switches should be same. If it is not same, that means the data is corrupt. Okay, the integrity of this data is compromised and the data has been tampered. This is what it means if the frame check sequence are not equal. And that is what frame check sequence does. All right, so let me give a recap of the header over here. Okay, so the Ethernet header contains a preamble field, SFD field, destination MAC, source MAC, type field, data field, and frame check sequence field. The format of a preamble field of is alternate ones and zeros. 56 bits of alternate ones and zeros. A start frame delimiter format is also same with an alternate ones and zeros. However, the last bit, the 8th bit, is 1. Now, the work of a preamble and SFD field. The work of a preamble, the work of the preamble and SFD field is to let the networking device know that a new Ethernet frame is being received and the switch or the networking device is reading a new frame. And when it finishes reading preamble and SFD field, it will read the destination MAC and the source MAC of the new header. Okay, the destination MAC and the source MAC may be same. Of the new header, the destination MAC and the source MAC may be same. However, it's a completely different header. All right. So preamble and start frame delimiter tells the networking device that a new frame is starting and they are going to read a new data. Then the type field. We discussed what a type field is. Type field is very similar to the description of the package in our Amazon package, which basically tells the switch what kind of layer 3 data is being carried in the data field. All right. Then the next is frame check sequence. The last header is frame check sequence, which basically tells or the two switches compare their frame check sequence with each other. And if the frame check sequence is correct or it's at equal, that means the data is not corrupt. The data's integrity is not compromised and the data is not tampered. But if it is not same, that means the frame is corrupt, integrity has been compromised, and it has been tampered. This is what the FCS field does. And this was about the Ethernet header. This was about the Ethernet header. Okay. Now let us talk about the IPv4. Okay. Let us talk about the IPv4 header. So an IPv4 header. Okay. The length of this IPv4 header is 32 bits. We can see 16 bits plus 16 bits is a 32-bit header. All right. So it's a 32 bits length, not 32. Then it's the total size is not 32 bits. The length of this header is 32 bits, 16 plus 16. Now starting from the first bit. Let's start from the first bit. This is your version bit. Okay, version field or version bits. And because we are talking from an IPv4 perspective, this version will always contain an IPv4 as the version. Okay, IPv4. And because it is version number 4, we will always see the number as 1 0 1 triple 0. We will always see the number as 1 triple 0 over here. 1 triple 0. Okay, so 1 2 3 4 4 bits, which means 1 triple 0. Not 1 triple 0. I'm sorry. 0 1 0 1 0 0. I'm sorry. 0 1 0 0. 0 1 0 0. This is the binary format or binary form of number 4. Okay, which means this is an IPv4. Got it? So let me open up the Wireshark again and show you this particular thing. This is our IPv4 packet. Okay, version field, you can see version is always 4 because it's an IPv4 packet, version number 4, and the format is 0100. Okay, 0100. Then the header length. What does this header length mean? Okay, what is the total size of this header? It is 32 bits. It is 32 bits. Now, how many rows are there? 1, 2, 3, 4, 5. Leave these 2 rows as of now. Leave these 2 rows as of now. Okay, so 32 is the size. And how many rows do we have? 1, 2, 3, 4, 5. Okay, So 32 bits of 5 rows, or 5 rows of 32 bits, which gives us 160 bits. Okay, 160 bits. And if we convert this 160 bits into bytes, we get 20 bytes. Okay, we get 20 bytes. And let me open up Wireshark and show you header length. You can clearly see here header length is 20 bytes of an IPv4 header. Now, the question is, what does this header length mean? Header length, header length is the minimum IPv4 header size. It's the minimum IPv4 header size. Okay, and that is always and always 20 bytes, which means that all these fields that we have seen in this, we will see in this 5 rows. Okay, these data or these fields in the 5 rows, okay, together make 20 bytes. Okay, so that means in an IPv4 header, all these fields should be present in order to make the minimum header of an IPv4 as 20 bytes. And any byte less than 20 bytes, means that it's an incomplete IPv4 header. It's an incomplete IPv4 header, or it's a wrong IPv4 header. Okay, so the minimum size of an IPv4 header is 20 bytes, and now we know how is it calculated. All right, so 32 bits, okay, multiplied by 5 different rows, leaving the last 2 rows, okay, gives us 160 bits, and if we convert it into bytes, we get 20 bytes, which is the minimum header length or header size of an IPv4. Got it? Then the next is types of service. Types of service is also called as QoS. QoS, or quality of service. Quality of service. Now, what does quality of service mean? To give you a high level explanation of what a QoS means, that, okay, imagine this is a road. Okay, this is a road. Okay, and there are different cars on the road. Okay, a different or many cars on the road, and suddenly there is an important vehicle, or let's say that there is an ambulance. Okay, there is an ambulance on the road. It sees the traffic. It sees the traffic in front of it, and to move faster, in this traffic, what will the ambulance do? To move faster, what the ambulance is going to do? Ambulance will basically blow the siren. Okay, it has a typical siren, right? It will blow the siren, and it will also start blowing horn as well. Okay, siren and horn. These are the two important things that an ambulance has, right? When any other vehicle sees the siren and hears the horn, what they will do? They will make way for this ambulance so that the ambulance can go through between them and can move faster. Correct? So over here, these vehicles are your normal cars or normal traffic. But an ambulance is a special vehicle. Okay, it is a special vehicle. And for special vehicle, when it uses its siren and when it starts to blow horn, the normal cars are supposed to give way for the ambulance to pass. Right? This is the rule that is written. Similarly, in networking also, imagine this as the wire. This as a wire which has some bandwidth. For example, 100 Mbps is the bandwidth or the speed with which the data can, or is the size. 100 Mbps is the size of this wire. All right. Now there is data going. There are normal data that is flowing through this wire. Suddenly there is an important traffic that needs to be sent. Okay, these are normal traffic. Now, when I say normal, the discussion, the Zoom call that we are having is a very normal traffic. The call that we are having, the Zoom call, my video, my screen, my voice, everything is flowing through the internet, but as a normal traffic. But as a normal traffic. Okay. Suddenly, on the internet, among the normal traffic, there is a government data also flowing. There is a very specialized government data or a very a government or a military or a defense data that is flowing. It will be marked special. That data will be marked special. And when that data flows in the wire, all the normal data, all the normal data will be less preferred by the device. And how is it? And how does this work? Let me give you an example. So imagine this as a router. Okay, this is a wire, and there's a lot of data that is coming to the router, and the router is also sending that in. Okay, there are a lot of data that is coming. Right. Suddenly, there is an important data that comes to the router. Right. So what the router is going to do, router will prioritize this data to be forwarded first before any other data. The router is going to prioritize this red data over the black data, and it will forward the red data first before sending out any other data. Right. So what is happening? This red data is a special data, is a special data. And how is an ambulance made a special vehicle? Okay, because it has a siren and it blows a horn. These siren and horn, the way it blows horn is not used by regular vehicles. Similarly, in networking also, to prioritize a particular data, you use special features. And that special feature is basically your QoS, quality of service fields in the IPv4 header. If you have a quality of service, if your data is important, your QoS field will have some value. And when it has some value, this particular data will be prioritized by the router over any other data. Okay, so let me take you to the field over here. This differentiated service field. Okay, this is the QoS field or the TOS field that we were talking about. You can see it is 0, 0. That means my data over Zoom is not a priority data, it's a normal data. And if it was a priority data, we would see some different numbers over here. Okay. And if my data is prioritized, or if my data has some fields over here, number over here, my data will be prioritized by any router which is reading my data. It will prioritize my data first, then other data that it has received. That is the work of QoS. All right, quality of service. I hope that QoS is clear. Then the total length. Total length is including your options field and your data field. Options and data field gives the total length or the total size of your IPv4 header. Your normal header length was only 20 bytes, correct? Was only 20 bytes. But the total length is your header length, is your header length plus options plus data. This is your total length of the IPv4 header. Okay, so you can see total length 1224. Okay, 1224 bytes. Okay, 1224 bytes, which is obviously greater than 20 bytes. So that is the total size of the data that is being sent from my laptop to onto the Zoom server. Okay. Now, next is your identification field, 0, DF, MF, and fragment offset. Before we jump into this particular row, let me give you a scenario. Okay. Okay, even before that scenario, let's try to understand a particular term which is called as MTU. MTU means maximum transmission unit. Maximum transmission unit is MTU. Okay, MTU, maximum transmission unit. And what does maximum transmission unit mean? A router is there. Router has an interface with a wire connected to it. Let's imagine fast Ethernet 0/0. Okay, now out of this fast Ethernet 0/0, what is the maximum size of data R1 can send? Okay, R1 can send in 1 second. That is your maximum transmission unit. Okay, this is not related to your 100 Mbps of bandwidth. Okay, 100 Mbps of bandwidth is different, MTU is different. Okay, 100 Mbps is a collection of different MTUs. For example, by default, every Cisco router in one, not in 1 second, sorry, in one single shot. Okay, in a single go. I should write as in a single go. Okay, maximum size of a data that R1 can send in a single go out of fast Ethernet 0/0. Okay, that is your MTU. Okay, now what does this mean? By default, every Cisco router has an MTU of 1500 bytes. What does this mean? MTU of 1500 bytes. It means that a single data or a single frame or a single data that R1 sends out of fast Ethernet 0/0 is only of 1500 bytes and not more than that. This means that multiple 1500 bytes, 1500 plus 1500 plus 1500, there are multiple data of 1500 bytes together combines to 100 Mbps. Okay, so that is what I was trying to tell. Your bandwidth is different and MTU is different. Okay, your bandwidth comprises of many data that are equivalent to MTU. Okay, so the maximum size of your data that the router can send, okay, can send, not receive. Please, we will always consider MTU when we are sending the data. When the router is sending the data, we will always consider MTU when the router is sending the data, not receiving. It is always considered when sending the data. The maximum size of the frame that the router can send is called as the MTU, maximum transmission unit. By default on Cisco devices, it is 1500 bytes. You can change it. You can change it to a lesser byte. You can change it to a lesser MTU. You can change it to a higher MTU as well. But MTU is not equal to 100 Mbps, which is the bandwidth. Multiple different sizes of MTUs together combined to a bandwidth of 100 Mbps. Okay, I hope that differentiation is clear. Okay, now since we have understood what an MTU is, let's try to understand that row where identification field 0, MF, DF, and fragment offset is present. Okay. Now, MTU. Let's imagine that there are multiple devices, R1, R2, R3. Okay. Imagine that R2's this interface has an MTU of 500 bytes only. 500 bytes. Okay. R1 is sending a data to R3. Okay. R1 is sending a data to R3. When R1 sends the data to R3, the size of that data is, for example, 1500 bytes. Just 1500 bytes. Okay. Now, R1 send the data to R2. As I said, MTU is considered only when sending the data, not receiving the data. So R2 has received the data of 1500 bytes. But when R2 has to send this data to R3, it cannot send more than 500 bytes at once. It can send only not 1500 bytes. It can send only 500 bytes at once. It cannot send more than that. But the data it has received is of 1500 bytes. So now what what R2 has to do? R2 will segregate these 1500 bytes into smaller 500 bytes of data. Correct? Okay. 500 bytes of data, 500 bytes of data, 500 bytes of data. All right. Now, this 500 bytes of data will be one IPv4 header. This 500 bytes of data will be another IPv4 header. This 500 bytes of data will be another IPv4 header. Now, these three different frames or IPv4 headers will be sent to R3. Will be sent to R3. Now, R3 receives these IPv4 header, but how does R3 understand, or how will R3 know that these three different frames or three different data, IPv4 data, are actually one single data which have been segregated, correct? Which have been segregated into three different 500 bytes of data. But if you join them together, they are the actual 1500 bytes of data that R1 sent. How will R3 know it? That is where your identification field comes into picture. So R2, when R2 is sending these 500, 500, 500 bytes of data, it will mark all these IPv4 header with an identification mark. Let's say that identification mark is A. A. Okay. So in all these 500 bytes of data or IPv4 header, there will be an identification mark of A. Now, when R3 receives it, it will understand that, okay, that means these 500 bytes of data are part of a single data and they are all marked with A. So I have to reassemble them together first. All right, that is the work of identification. All right, then you have a fragment offset field. Fragment offset field. Now, when R3 is receiving these 500 bytes of data, let me make this as frame number, data number 1, data number 2, data number 3. It is not necessary that R3 it is not necessary that R3 will receive these frames 1, 2, 3 in a sequential manner. It can receive as 1, 3, 2, or it can receive as 3, 2, 1. It can also receive as 2, 1, 3. It can receive as 3, 1, 2, etc. Any combination is possible. Okay, any combination is possible. It may receive in a sequential manner. It may not receive in a sequential manner. What if it does not receive in a sequential manner? Okay, if it does not receive in a sequential manner, the data will not be read properly. It will be gibberish for the router. So it is important for the router to reassemble these data in a sequential manner. And reassembling this data in a sequential manner is the work of the fragment offset field. Is the work of the fragment offset field in an IPv4 header. So the fragment offset field of frame number 1, frame number 2, sorry, data number 1, data number 2, and data number 3 together will help R3 arrange these packets in a sequential manner so that R3 can combine these three frames together and make it one big frame once again. That is the work of fragment offset field. All right. I'm going to skip don't fragment field, more fragment field for now because it will complicate stuff. It will complicate stuff. Okay. So just remember that this don't fragment field and more fragment field again comes into picture when you have this kind of scenario, fragmentation. Okay. This whole scenario or example that I gave you is called as fragmentation. This is what you call as fragmentation. Dividing a bigger packet into three smaller packets is what you call as fragmentation. Okay. Fragmentation and reassembly. And reassembly. What does reassembly mean? Again, combining all these different packets into a single packet is called as reassembly. So your don't fragment field and your more fragment field comes into picture when you have fragmentation and reassembly. Okay. As I said, I'm not going to discuss don't fragment and more fragment field because it will unnecessarily complicate what I've explained. Okay. But I hope what does an identification field and fragment offset field do in an IPv4 header is clear. Okay. Now, now let's move on to the next row, which is your TTL, time to live. Okay. Now in the switching part, when we were discussing loop in the network, we had one switch, two switch, and three switch, and we discussed how a loop is formed. Okay, how a loop is formed between three switches. And to avoid this loop, okay, spanning tree was created. Correct? A spanning tree was created. But in a router environment, if we have R1, R2, okay, and R3 over here, okay, and R1 sends the data to R2, R2 sends the data to R3, R3 will send the data to R1 for some reason. So basically, even in your layer 3 network, also, you can form a loop. You can form a loop. And there is no such protocol like spanning tree protocol in layer 2 network. There is no such protocol in layer 3 which can help us avoid these loops or which can give us a loop free layer 3 network. There is no such protocol. And to avoid a layer 3 loop, okay, a layer 3 network loop, in an IPv4 header, we have this field time to live, or we call it as TTL, time to live. On Cisco devices, this TTL value is always 255. Okay, so let me open a Wireshark. Okay, we can see TTL is okay. This is from a Windows device because my laptop is sending data from the OS that is running is Windows, so the time to live value is 128. But on Cisco devices, it is 255. Okay. Now, what does this 128 or 255 basically mean? So let me draw those three routers once again: R1, R2, and R3. Okay. So when R1 sends the data to R2, R2 will receive it. R1 will send the data with a TTL value of 255. R2 will receive this data. R2 will forward the data to R3. When R2 forwards this data to R3, it will decrease the TTL value by 1, thereby making this TTL value as 254. Okay, R3 will receive it. R3 is going to forward that data to R1. When R3 forwards it to R1, it will decrease the value to 253. Okay, then again R1 receives it. R1 will forward it to R2. Now decreasing this 253 to 252. Like this, every time the router forwards the data, the TTL values decreased by 1. the TTL value is decreased by 1. And when the TTL value reaches 0, when the TTL value reaches 0, the packet is dropped. The packet is dropped when the TTL value reaches 0, thereby avoiding the loop in layer 3 network. Thereby avoiding the loop in layer 3 network. Okay. So since we do not have any protocols like spanning tree protocol in layer 3 network, we use TTL in an IPv4 header to avoid the loop. So whenever a router forwards the data to another router, it will decrease the TTL value. Okay, it will decrease the TTL value. So the TTL value on a Cisco device is 255. It starts with 255 only. On Windows device, we just saw it is 128. It is 128, right? So when a router forwards the data to another router, it will decrease the value to it will decrease the value by 1. And if for any reason the data does not reach the destination router and the value reaches 0, that packet is dropped. That packet is basically dropped. Okay, this is the work of TTL. Now next is your protocol field. Okay, the protocol field in an IPv4 header is very similar to what the type field does in the layer 2 header. Let's go back to our type field. What did the type field do in the layer 2 header? Type field tells the layer type field tells the switch what kind of layer 3 data is it carrying. Correct? What kind of layer 3 data is it carrying? Similarly, your protocol field in your IPv4 header tells what kind of layer 4 data is being carried. What kind of layer 4 data is being carried. In your layer 4, you have two types of fields. You have two types of data, a TCP, transmission control protocol, and UDP. Okay. TCP and UDP. These are the two types of protocol that is in the transport layer. So is it a TCP data or is it a UDP data? TCP is transmission control protocol. UDP is user datagram protocol. Okay, is it a TCP protocol? Is it a UDP protocol? We'll discuss TCP, UDP probably later in the course. Okay, what is is this data that is being carried? Is it encapsulated by a TCP data or is it encapsulated by a UDP data? That is what the protocol field tells, which is, as I said, which is very similar to the type field in an layer 2 header. Okay, then the next is your header checksum. Header checksum is equivalent to your FCS field of a layer 2 header. What did the FCS field do in layer 2 header? It basically checks the integrity, the corruption of the layer 2 header. Similarly, header checksum also does the same thing. Header checksum again checks the integrity and the corruption in the IPv4 header. Okay, the working is same. It will create an algorithm, find out if the algorithm value is same. If the algorithm value is same, okay, then the data is accepted. If the algorithm value is not same, the data is not accepted. Similar, very simple. Okay. Then we know what a source IP is. We discussed in the static routing what a source IP is, what a destination IP is. I will not discuss option field and data field as of now. Okay, because it will again unnecessarily complicate the discussion over here. Okay, so version tells what kind of IP header is it? Is it an IPv4 or an IPv6? And in an IPv4, it will always have an IPv4 number. Header length, the minimum size of your IPv4 header, which is 20 bytes. Types of service, which is a quality of service. If your data is a priority data, it will have some value. Total length, including your options field and your data field. The total size of your IPv4 header is your total length. Identification field, DF, don't fragment field, MF, more fragment field, and fragment offset. These four fields come into picture when we have fragmentation and offset. And fragmentation and offset is done based on MTU. Okay. Time to live is used to avoid loop in the layer 3 network, where time to live value for Cisco device starts with 255. And when the router forwards the data to another router, it decreases the TTL value by 1. And when the TTL value reaches 0, the packet is dropped. Protocol field tells the router what kind of data, what kind of layer 4 data is being carried. Is it a TCP data or is it a UDP data? Right. Then header checksum basically uh, basically verifies the integrity of your IPv4 header. We know what is the source IP headers and what is destination IP addresses. Okay. So this was about your layer 2 header or your Ethernet header and IPv4 header or your layer 3 header. This whole session, okay, this one particular class is a very, very important interview session as well. So please make sure you go through this again and again in order to understand your layer 2 and layer 3 header from an interview perspective as well. All right. So thank you and have a great night. I'll see you guys tomorrow.